Okay, YouTube, in this video we're going to be discussing and exploring continuous growth models. In the past, we have explored growth models that are, n compoundings per year. In this situation, we're going to be looking at continuous growth models, that is, growth models that compound infinitely many times, okay? So let's go ahead and start with that. We say previously we learned that an amount A in an account earning interest compounded n times per year for t years is given by this guy right here. So essentially, this is some exponential model. We say y equals a times b to the x kind of, where this is our base b. This is our initial amount a. We call this the principal amount. And we said that y represents the amount in the account after a given amount of time. R was our rate, and n was the number of times it compounded per year. What I want to basically articulate here is this. We looked at the number n before, or n, sorry, the number e before, and we said that this quantity right here, which by the way looks eerily familiar here, they look very, very similar, as x gets extremely large, then this right here basically is approximately e, which is approximately 2.718. So that is to say, let's imagine we have an account that doesn't compound one time per year. That is, we would say one time per year would mean that our n is 1. If we compounded monthly, that would be 12 times in a year. If we compounded daily, we would say that n could be 365.248-ish. But what if I were to say we're to compound every minute of every day, of every second of every minute of every day? Then we would say that n would become so large that we couldn't assign it a number, but what we could say is that this formula right here would actually approach this number e as n gets larger and larger. So what we say is this. For things that compound continuously, this is the key word here, continuously compounding interest or growth, continuous, okay, then we would say that the formula approaches this right here. So this is the formula for continuously compounded interest. It is also continuously compounded growth or decay. You're going to hear both of these today, but essentially whenever you hear the word continuously, we're saying we're using this right here. So let's go ahead and pick it apart. We say that A is very much the same thing. A is the amount after t years, okay? We say P, this is the principal amount. In other words, this is what you start with, and this is very similar to anything we do with exponential functions of this form. We say the A value is what you start with. R is going to represent our rate, and it is a percentage as a decimal. That's very important that you list it as a decimal value. And then T is time when you talk about interest, and we're going to say, specifically years in this case. But we can always write a continuous growth model by saying essentially y equals AE to the RX, more generally speaking. When you're not talking about money, we don't use amount here and we don't use time here. But this is essentially the same thing. And whenever you use continuous growth, we just assume that the base of this exponential expression here, B, is set equal to this number 2.718, or E. Okay, so let's go ahead and put together a couple of growth models here and represent them graphically and use them to make some predictions here. But let's say we consider a mutual fund that we have. It compounds interest continuously at a rate of 3%. And now, here's the first thing I want to point out is this. It compounds interest continuously. I did not say so many times a year. I said all of the time. So we already are tipped off that we're going to be using this A, A equals PE to the RT, or PERT. That's how you can remember it, is PERT, okay? So we'd say it does this at a rate of 3%, so we already are privy to the information that this is 3%, or 0.03 for our R value, and we have a principal amount of $10,000 in the account. So we say P is equal to 10,000. I'm not going to put a comma there. This is also our A value, essentially, in a growth model. So it says write a continuous growth model for the amount A in the account over time T in years. So when somebody asks us to write a continuous growth model, we already know we're using this, and I only need to know two things. What are you starting with, and what is the rate of growth? So we're going to say that the amount A, we're going to say A, is equal to $10,000 is what we're starting with, times the base E, that's our continuous part, and then we say that this is to the RT, where our R in this case is 0.03. So we have 0.03 T. So now one thing I do want to say about this, a couple things actually, is I'm going to say that it's the same thing as 10,000 e to the 0.03x. This could go into a calculator just fine, but we use a and t to represent something when we talk about money. And the other thing here is this. When I underline the word model twice, I was saying that this is a model. That is to say that this will tell us more generally what our amount might do over time t, where time is not necessarily specific yet. So we want to be keen on writing models in the first place, because what we want to do is use that model now to predict the amount that's going to be in the fund after a given amount of time, as I mentioned before. So for instance here, if I said, well, after 10 years, notice that I've given us a time value here. So what I'd like to do then is take that time value and substitute it into our model and say, well then, what is this amount going to be? What is the output when we have 10 years? So let's go ahead and run a calculation on this. We say, well, the amount would be equal to the 10,000 that I started with, compounded continuously at a rate of 0.03. Now that 0.03 is our rate, but our time now is 10. So if I'm going to do this on a calculator, let's go ahead and trace my steps here. Now, nicer calculators than this one, so this one will work better, but we say I'm going to do 10 times 0.03 first, so there's our 0.3 in the exponent. We're going to do e to the power of this. So e to the power of 0.3 is all of this. We're going to take that times 4 zeros. So we get $13,498.58. So $13,498.50, I think it was 58 cents-ish here. So after 10 years, if compounded continuously to 3% rate, we will have made about $3,500 almost, okay? So what we want to do here is this. We want to create a rough sketch of this function. We're going to label the y-intercept and the amount after both 1 year and 10 years. So now we've already found 10 years. We're going to have to go back and find 1 year. But in terms of what this graph would look like, let's go ahead and put on a few key details. Of course, we are used to x and y, but in this case here, this y and this x are represented with an a and a t. So let's go ahead and start with what's down here. This is our time. And remember, we're measuring this time in years. So this really is, instead of x here, it's our t variable. And we say that this is the amount given at a given time. So amount is a function of time, so we're going to say the amount over time, and this is being measured in dollars. So let's go ahead and start with a few key or clutch points here. When you graph something exponential, we say x and y, and I can write this up here. We say time and amount at that time. We should always start probably with a few key points here. Now, 0 being one of them. 0. Now, if we were to plug in 0, we would get y. Where's our model here? Here's our model over here. So we would get y equals 10,000 e to the 0.03 times 0. Now anything times 0 is 0, so this is going to become a 0. E to the 0 is 1, and 1 times this here is our 10,000. So essentially, when we start off here, we're starting off with $10,000. Now, when did this happen? It happened at time 0. So I am going to label this. I am not going to include commas here on this 10,000 because I don't want to confuse it in this ordered pair for being a part of the ordered pair. But essentially, that's this point right here, and it represents at this time we had this amount. So we wanted to graph a couple of different amounts here. We said at 1 year, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now I know at 10 years already it goes up to about $13,500. So that's 10,000, and I say that this would be like 20,000. At 10 years, we would say $13,500 would be about right here. We say that at 10 years, we have about 13,498.58, and we're going to figure this out at 1 year as well. So 1 year, into our model, we would have plugged in a 1 here instead of a 0. So 0.03 times 1 would be our 0.03. We'll take e to the power of that. We're going to take that times 10,000. So about 10,304. So I'm going to write this on our graph here at about 1 here. At 1 year, I should label this up here. At 1 year, we had about $10,304, and I'm just going to leave it at that right there. But our exponential growth function, even though I've stretched it out quite far, would not pick up so quickly as much as that, but it would look like, kind of like that, and this would be our amount over time. So when we say, what does this y-intercept represent? This is our principal amount. And in other words, we're saying that at time 0, this is what we started with, and everything to the right of this is telling you an amount at a given time. Okay, so let's take a look at one example really quickly here of a continuous decay model. So it says purchasing a new car should be considered one of the worst investments that can be made. The reason is because the car, once driven off the lot, we immediately have a decrease in value. It actually decays in value. So let's assume in this instance we purchase a car for $20,000. We say due to market conditions, the value of the car decreases continuously at a rate of 15%. I'm going to write a couple things down here, starting with this. We're starting with a $20,000 principal amount on this, and our rate here is 15%. So we say 15% or 0.15. So we want to say that this car decreases in value continuously. So for our growth model, here's our growth model. We said that we do tend to represent it thusly with PERT. But if it is a decay model, these are both growth, for instance, here. Recall that decay, in this case, is going to be anything that has a negative in front of its rate. So we would say in this case we are going to be writing PERT, but we say a negative in front of its R value. So our rate is certainly positive, but we put a negative out front on purpose to cause this to be decay. So what we want to do is identify that first and then say, well, write an exponential decay model that represents the value of this car A over time t in years. So we say the amount over a certain time is given as the initial 20,000 that we started with times e to the negative. Now we'll plug in our 0.15 in here, and you'll notice that I put the negative out in front of it. Again, this rate here is positive. It's just that we want this to be decay, so we're going to put that as a negative in front, and then we say over time. So this here, this is important. You usually get a point for writing just this right here. They say this is going to model the amount of money that our car is worth over time. So we're going to use this decay model to predict what our vehicle is going to be worth in 1 year, 5 years, 10 years, 20 years from the time it's driven off the lot. And the way we can do that is we can just simply plug in a time and find the amount at that time. So for instance, at 0 years, we would say that this would be $20,000. At 1 year, let's go ahead and calculate for 1 year. So we're going to need a calculator here. And we would say that really what we get is we would say A of 1 would be our initial 20 grand, e to the negative 0.15, and this will be, in this case, I'm going to say times a 1. So now if we did this to the first power here, we get negative 0.15 in the exponents. We're going to take e to the power of that, and we get this number here. We say take that times 20,000. So right off the bat, after a year, your car's only worth about 17,214. So we have 17,2. Let me get rid of this here. All right, so 17,214. So now we'll say, how about at 5 years? We'll go plug in a 5 right here. So after 5 years, how much would this be worth? So again, our calculator, we're going to have to do what's in the exponent first. So we'd say 0.15, which is negative. We're going to take that times 5. We're going to take e to the power of this number, and we're going to take that times 20,000. So now, after 5 years, it's only worth $9,447, so 9,447. Let's do after 10 years, what is this car worth? So now we'll plug in a 10 right here, 10. And we'll say, okay, well, what would we get? Well, negative 0.15 times 10 is just going to scooch our decimal there. We're going to take that to the, e to the power of that. We'll take that times 20,000. We get about $4,462. So I know that I wanted to find the value of this car after 20 years, if it lasts that long. But the idea here is this. You can see how this car, in the first year, it just went down that much. And even in the next year, it's going to go down a lot. So I'll always tell people, buy a car that's 1 or 2 years old already and let somebody else pay that initial depreciation, and then you can hold on to it while it depreciates less rapidly here. Okay. So we were able to find these values here. Again, you should go through and find it for a value of 20. What we want to do now is create a rough sketch of the function, labeling the y-intercepts and the amounts we found in part B. So if I'm going to look at the value of this car over time, I'm going to start with this. We have time and the amount that it's worth at that time. And I noticed that our peak amount was 20,000. So I'm going to go down. I will say that half of that would be 10,000. Halfway between those would be maybe like 15,000. Halfway between those would be, of course, 5,000. And we put on some times here, starting with 0. 0 comma 20 grand would be right here. After 1 year, just 1 year, we say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We would say that it was worth about 17,000, a little bit less than 17,500. So it would be about right here. And then after 5 years, it was only worth a little less than 10,000, so it would be about right here, tracing it over. And after 10 years, only worth a little less than 5,000, so it would be about right over here. So if we were to look at this, on a computer-generated graph, we could see that the value of this car is decaying over time. We wouldn't know, kind of outside this range what it would be doing without finding those things, but here's our decay model. And we could use it even to make predictions about times, like after 7 years, how much our car would be worth. We could get a good idea what this is worth. Okay, cheers.